here. Let me introduce Eduardo was a researcher at Microsoft Research and worked with Kevin, was Kevin's internship mentor 5 years ago at Microsoft Research. So we have Ang is a system professor in computer science. Dan Wallach is a professor in computer science. Eduardo, you're with Facebook right now, right? Oculus.
Yeah,
Okay.
I'm full on into VR now.
Okay, good. That's very cool. That's very cool. Let's see if Dan is back.
Yeah, he's back. I'm
okay,
back.
Cool. I think we can get started. All right. So Kevin is going to be my last Rice PhD student to get the Rice degree. So he's going to talk about the operating system he has been working on for the past 4 years. Okay, Kevin, go ahead.
Sure. Yeah. Thanks everyone for attending. If anyone's on the chat who doesn't know me, I don't think that's the case, but my name's Kevin Boos. Today I'm going to talk about the work I've been doing. It's only over the last 3 or so years that I've been working on Theseus, but still a long time. And I talk about the work we've been doing to rethink the fundamental structure of operating systems and how they approach state management for the benefits of things like evolution and flexibility and availability. So our key hypothesis is that fundamentally redesigning an operating system to avoid state spill will make it easier to evolve and also make us able to do it more arbitrarily, as well as to recover from faults. And a side question we have during this hypothesis is how much can we leverage the power of language and compilers to help with this goal? So in a nutshell, before we go any further, I just want to describe Theseus overall. There are 3 design principles we follow. The first one is to establish a unique OS structure in which there are many tiny entities and they have runtime-persistent bounds, and all entities have that. The second is to empower the compiler and leverage its strengths. We want to go beyond language safety to adopt an intralingual OS design, which means implementation within the language, which will allow us to shift the responsibility of resource bookkeeping from the OS to the compiler. And then thirdly, and most importantly, we want to avoid state spill. While doing this, we design with evolvability and availability in mind. And just to give you a current idea of what Theseus looks like, it's just under 40,000 lines of Rust code, which we've written from scratch, and about 900 lines of assembly, which is just used for Bootstrap before we get to the Rust file. So let me give a brief outline of my defense. First, I'm going to talk about why, our motivation, our goals, and the related work that's relevant to Theseus. Then I'll talk about its structure and design principles. I'll give some examples, brief examples of 2 specific subsystems, namely the core subsystems of memory management and task management. And then I'll talk about how these design principles and the intralingual implementation help realize evolvability and availability through fault recovery. Then I'll talk about some other evaluation concepts beyond those 2, like the cost of intralingual designs, and then briefly conclude with some limitations of discussion. So first up, why Theseus? So initially, this work was motivated by our study of state spill, which I did about 4 years ago, and that was published in OSes 2017. It basically identified the phenomenon of state spill, which is a term that we've coined. And what state spill is it's when a software entity state undergoes lasting change as a result of interacting with some other entity. Right? You may be wondering, what is the state of a software entity? Well, here we just mean something relatively casual, right? It's the set of program variables within the scope of a given function or a class or a whole program, whatever your entity may be, right? And then the values of those variables within scope. We found that state spill was a root cause of many challenges and hindered the realization of various computing goals, from things like fault isolation and tolerance to live update, maintainability, software virtualization, process migration, and more. So before I go any further, just let me give you a brief example of state spill. So let's imagine we have 2 applications, A and B, which are interacting with an operating system service. It could be a driver or something. Application A communicates with it and perhaps sends some configuration states or something, and the OS service holds on to those for future use. It does the same thing with application B. Now let's imagine during the interactions, the OS service dies. It's corrupted, it crashes, something like that. So a typical approach would be to replace it with a new instance of that OS service, right? This is commonly used in pretty much every system from microkernels to Android. Oh, can you guys hear that background noise? I hope not, because they're washing the windows right outside my my unit. It's very loud. Okay.
We're fine, Kevin. Just continue.
Okay, good. Yeah. So the common approach is to respawn a new instance of that OS service. Then the problem is it will be missing those states that applications A and B expect to be there. Right? Now, this inconsistency causes a hard crash in the best case, right? A very quick panic or oops. And in the worst case, it can just silently propagate as undefined behavior. So beyond state spill, we have other areas that we're motivated to improve. Like I mentioned, our two top-level goals are evolvability, which is effectively the temporal version of live evolution or live update, and then the spatial aspect of runtime flexibility, which I'm not going to touch on in this defense, but it's part of the thesis. And then we have availability, which is effectively just fault recovery. Right? We're also inspired by Rust's goals of compile time safety. Basically, they achieve a lot of things at compile time, memory, and type safety, and we were inspired to say, how can we exploit these features of more powerful language like Rust to do even more things at compile time and relieve the burden, relieve the OS from the burden of doing some of these things like resource management. So we believe that Theseus can go further than existing works based on its new angle of looking at state management. So just to do a brief comparison with related work, existing live update approaches either are difficult to use or they're not arbitrary. Right? And what I mean by that is that any layer, any entity at any layer of the system can be evolved and changed at runtime. Okay? So K42 was one of the, I think, most significant implementations and explorations of live update. They refer to it as hot swapping, but their goal was to hot swap different class objects, right, class instances in an object-oriented OS. They restrict hot swapping to the same base class where everything has to inherit from the same set of interfaces or an abstract base class. And they require a forced indirection layer to mediate between different instances of a polymorphic class or something. They also do not support evolving things like the underlying code that handles exceptions, interrupts, and hardware, anything beneath the language level. And this is a common theme that we see with many safe language OSs. Moving on to monolithic kernels, there's been a lot of approaches to retrofit existing monolithic kernels like Linux with live update functionality. But the problem is within the kernel itself, they lack clear bounds. And I'll describe this in more detail later. This makes it difficult to ensure consistency across different versions of changed functions and data structures. And also, all of these works like K-Splice, K-Patch, and all of these different commercial variants of those target very small security patches, right? And in general, they cannot change the user kernel interface, and they assume that it's stable, like the set of syscalls and that API. There's other approaches like K-up, which swaps out the entire kernel from underneath checkpointed apps, but that's a very heavyweight approach. And then finally, we have things like microkernels, which shift functionality into user space server processes, and then they generally only allow you to update those. This is the case with Minix, which I think the preeminent state-of-the-art live update system was implemented atop called Proteus, and they focus more on state transfer and evolving data functions. So we build on top of that, but it's not a focus of our talk. Moving on to fault recovery, in general, other approaches are either limited, inefficient, or coarse-grained. So Theseus' goal is to offer very fine-grained recovery that doesn't violate language level safety or isolation. It's intralingual, right? And it extends to cover entities within the very core of the OS or the kernel. There was an existing work called Curios, which was also an object-oriented operating system that recognized the problem of servers holding state for clients, which is effectively like state spill, but not quite the same. They didn't identify the concept of state spill, but they did use the MMU to provide hardware isolation between client-side and server-related states. Microkernels, like I already mentioned, they use server processes and can restart them to recover from faults, but that's a relatively coarse-grained approach. And then there are a variety of approaches that use software fault isolation and recovery. And they impose some overhead, for example, checkpointing and statefully restoring drivers that have gone down, or having interposition layers to check memory accesses. Okay, so that's kind of what inspired us to look at a new OS structure for Theseus. Now I'm going to talk about its overall structure and the design principles that we follow. So compared to other OS architectures, right, Theseus has sort of a loose bag of modules structure, right? Seen here on the left, right? Now this diagram shows the runtime bounds of system entities, right? I would say kernel, but the microkernel moves into user space, right? And any submodules that may exist, right? So if you look at Theseus, you'll see that it's not quite the same as any of these existing kernels, but it does have some of the benefits of monolithic kernels and microkernels as well. So in traditional monolithic systems, which is the second diagram here, you guys can see my mouse, right? Okay. In traditional monolithic systems, there is kind of a vague concept of entity bounds that exists most strongly at implementation time, but the entire kernel is fully statically linked together, and then you lose those bounds at runtime. Right? And there's a lot of containment hierarchy where you have submodules and submodules within other modules. The same thing is true for microkernels, although they move a lot of the functionality to user space, but the microkernel core itself is still effectively the same as a monolithic kernel. It's just smaller in scope. And then we have things like multi-kernels and kernels for heterogeneous architectures like K2, where we see the structure is based on the underlying hardware architecture, right? So it's actually quite similar to microkernels in that sense, where they base the entity bounds on processes, right? And one of the problems here is that you're stuck with using this hardware-defined entity bound and granularity, and you can't change the modularity of the system that easily in pure software. Right. So Theseus is made of many tiny entities. Each one is a cell. A cell is our terminology for it's a software-defined unit of modularity, right? It's effectively an individual project or compilation unit, right? The name obviously comes from biological cells, which are the core building block of organisms, just like a cell is the core building block of Theseus. And they're based on crates. And a crate is Rust's term for its project container. It's effectively just a set of source code and a dependency manifest, and it is an elementary unit of compilation. So if you have submodules or something in a crate, you still only can compile the entire crate at once, not the individual submodules, right? For that reason, we strive to keep crates elementary. And the thesis discussed this in more detail, but in general, we want to keep them as small as possible. So let's discuss the design principles now that we have an idea of the overall structure of Theseus. All right. First, requiring runtime persistent bounds for all entities. So the key point in how we realize this is that all cells are loaded dynamically at runtime, generally lazily upon first use of a cell. Not just drivers or kernel extensions like is commonplace in some existing safe language OSs like Spin, or even existing large commercial OSs like Linux or Windows, right? It's not just about drivers or kernels, it's about every single entity, even the core OS components. What this allows Theseus to do is to maintain and track the bounds of those entities and their dependencies. We generally just store things like the location, the size, and memory because we know exactly where that is because we loaded it at runtime and we linked it at runtime. And also bidirectional dependencies on a per section granularity. So in doing so, Theseus can construct this metadata tree, right? And this is effectively how we track runtime bounds and dependencies, right? So each one of these blue things is a loaded cell, which was loaded from a crate object file. It includes, some metadata, a list of sections, a list of memory regions, which is this MappedPages, which basically says where it is in memory and its size. And as you can see, there's up to 3 types, one for executable, one for read-only, and one for read-write, which is used for text sections, RO data, data BSS, respectively. And then all of these are loaded into kind of a namespace of crates and their publicly exposed symbols, which would be functions and data structure constructors and things like that. Right. So this is effectively how we realize runtime persistent bounds. Now you may be wondering, how do we actually obtain all of those separate crate object files so we can create cells at runtime? So Theseus splits the build process into 2 parts right before the linking stage. The compiler runs as normal to produce object files, right, which are not executable, they're raw object files. And then we go ahead and do the fully linked, fully statically linking process, but we don't actually use that executable here down at the bottom. This is a lot different than existing kernels like Linux and microkernels, which load this directly into the bootloader. And then they may have some additional loadable extensions or drivers. Everything here is loaded in as an object file, and then at runtime we link them, these object files, into the running system as cells. Right. So what this allows us to do is give a very consistent view of the form and the runtime balance of an entity. Right. At implementation time, here on the left, we see that it's a crate. Right. Each entity is a crate, and it has, as I mentioned, a dependency manifest and some source files. And then after compile time, at build time, we have object files, right? And there's a 1-to-1-to-1 correspondence here. And then at runtime, we have that loaded cell that I just showed in the metadata trees. Right? This is really nice because it allows both developers and the OS logic itself to observe entities from the same viewpoint. And the reason why that matters is it offers, a well-bounded, clearly identifiable unit for change that is visible across the life cycle of development. We have fully accurate metadata, and this generally reduces the complexity of the human mental model, which in turn makes evolutionary logic simpler and safer, and it offers a clear boundary of isolation, which is crucial for fault recovery. Right. So you may be wondering, how do you actually run a system that is completely loaded at dynamically at runtime? Obviously, you cannot execute an unlinked object file, so we have to bootstrap Theseus with what we call the nanocore. The nanocore is basically a kernel base image that is effectively a minimal set of crates, just a few crates that are statically linked together, such that the bootloader can jump directly to them and it can actually run. It includes just these pieces of functionality here. Just bootstrap the OS to set up a bare bones virtual memory environment such that we can load crates. And this isn't really a barrier to evolution, because we fully replace all of the nanocore's constituent crates after it's done bootstrapping. So we have a completely dynamic system. Now, comparing this to other minimal systems like microkernels, we can see that we're actually significantly closer to a theoretical minimum than microkernels, even though they purport to move policy and mechanism decisions out of the microkernel. Okay. Moving on to the second design principle, which is empowering the compiler. And the main way we achieve this is through intralingual OS design. So our goal here is to maximally leverage and empower the compiler. And this goal stemmed from my idea of just why not take advantage of all of Rust's powerful abilities, right? The more that I used Rust, the more I realized that it's very powerful. It can check many, many invariants based on its various built-in rules and models for type and memory safety. And the goal was, can we extend the applicability of these invariants to parts of the OS, parts of the system beyond just the stack and the heap, which Rust already has built-in models for. If we can do this, then we allow the compiler to take over resource bookkeeping, which in turn frees the OS from the burden of maintaining bookkeeping states, which obviously in turn reduces state spill, and it also strengthens isolation. So this can be very beneficial. Another interesting aspect is that it makes kernel development kind of beginner friendly, right? So we've had a lot of undergrads and younger folks who don't have OS or systems programming experience, and using this structure and the safety of Rust and intralingual design, they've been able to make meaningful contributions, which I think is quite a strong argument for an operating system. So what can Rust already do for us? A lot of things. I'm just going to go through this briefly. I figure most people are familiar with Rust or other safe languages. Right? It offers type and memory safety, which obviates whole classes of bugs. Right? Things like use after free, double free, buffer overflow, concurrency bugs. And this is based on Rust's fundamental notion of ownership of an object or a value. Right? Every value has a clear singular owner. For example, the function that creates a local variable owns that local variable. And this is based on the notion of affine types. Again, we can get into this later if you have questions, but I'm going to go ahead and skip the rest of this. There's a lot of things that it can do. I mentioned concurrency bugs. It has kind of a key rule, which is aliasing XOR mutability, which means you can either have multiple immutable references to a given value of memory, or you can have a single mutable reference, right? Or borrow, as Rust calls it. But you can't have both at the same time, right? So this is the key rule for compile time enforcement of memory safety. It also has strict semantics for moving or sharing data between threads. It avoids uninitialized variables, etc. But deadlock is still possible. So to empower the compiler, we break this down into two steps. The first step is we need to match the compiler's expected execution model of its code, and then we need to intralingually design and implement OS components such that the compiler can understand their semantics. So first up, matching the compiler's execution model. Now, I think this is relatively simple. Basically, pretty much every general purpose compiler expects that the output, its code output will become an executable program or part of one that runs within a single address space and privilege level, effectively within, for example, a single user space process. This is very common, right? So we're trying to match that in Theseus. Therefore, the Theseus OS environment is a single address space and a single privilege level environment. Everything runs within a single set of visible virtual addresses, and all within ring 0. Right? We establish a bijective, also known as one-to-one mapping, from virtual to physical addresses, such that a single physical frame cannot be duplicitously mapped by multiple virtual pages. And the reason for that will become apparent in the future, but basically it's to ensure memory safety. We also do some other small things to match some of Rust-specific expectations. For example, it expects a single global allocator instance, but we're still able to implement multiple heaps, for example, per core or per task heaps within that single instance. So I think that's pretty simple, so I'm going to stop there and move on to intralingual OS design. In a nutshell, the idea is to use safe code as much as possible. That's a given. But we also want to go beyond safety. Right? So what can we do beyond simple memory and type safety? We want to express the semantics of a particular OS resource or component using existing language level mechanisms. We want to preserve the language level context with lossless interfaces that don't discard type information and ownership details. And we want to prevent resource leakage, which can also prevent deadlock in some cases, by ensuring that all things are freed via stack unwinding, which we implement in Theseus. So first up, how do we express the semantics of the OS within the language, intralingual? First up, we need to identify the invariants for safe usage of a resource and ideally also correct usage. We want to prevent as much incorrectness as possible. We implement the semantics using existing language level mechanisms rather than reinvent our own mechanism or use mechanisms beneath the language level. For example, sharing memory by having two virtual pages mapped to the same frame is invisible to the language. So that's a black box of memory sharing. We want to remove these gaps in the compiler's understanding of the code behavior that we often see in safe language OSs so that we can approach something like end-to-end safety from an application all the way down through the entire software stack to the very lowest level right above the hardware. Right? And then if we do those first 2 points, we can allow the compiler to subsume those OS or resource-specific invariants into its already checked invariants for the stack and the heap, for example. This effectively tricks the compiler into checking our own custom invariants for the OS function, just as it does its type and memory safety invariants. Right. So a lossless interface is next up. Effectively what this means, it's not lossless in terms of like losing data, it's lossless in terms of losing language level context. For example, type information, the lifetime of a given object, ownership status, right? Are we passing it by reference or value? And this applies to both external facing functions for a given OS component and also the internal functions. We want to preserve that throughout. A corollary of this is that the provenance of that lossless information, of that type information must be ensured statically. And what that means is that we're not doing something like breaking and then extralingually recreating this type context from nothing. For example, system calls are lossy, right? At the application or the library level in user space, you're invoking a particular set of kernel functionality, right? And the best that you can do is ensure that you, the human, is the last line of defense to ensure that the types information, ownership, lifetime is preserved across that gap, because we're losing information when we convert things to raw values that are passed in registers for system calls. Right? So something like that is what we want to avoid. Moving on, we want to prevent resource leakage, and the way that we do that, obviously that goes beyond safety, but the way that we do that is by implementing custom stack unwinding within Theseus. Right? What this allows us to do is, if we implement resource cleanup semantics within Rust's concept of destructors, which is called drop handlers, then we can allow the compiler to ensure cleanup will occur for all acquired system resources. And this is really, really convenient because it effectively automates and removes all OS and developer effort from, tricky corner cases of ordering release operations. It's very nice. At a higher level, it relieves the kernel itself from the burden of bookkeeping resources. And we refer to this loosely as blind and distributed bookkeeping, right? Effectively, the OS lacks specific details of the resource or its cleanup routine. It knows that one exists, but it doesn't know exactly what that is, right? And it's distributed in the sense that there's not a monolithic central like task structure, something that bookkeeps all of these resources. Each task or client bookkeeps the resources for itself merely by virtue of it owning a particular resource. And this sets us straight towards the path towards eliminating state spill. Right? Also, it's the best way, and arguably, I would say the only way, to ensure fault isolation in a safe language OS. Right? We need to make sure that we're not, invalidating the safe language's expectations by doing things like failing to release locks, decrement ref counts, or release allocations. Right? And this is important when you have multiple tasks and execution contexts operating within the same single address space that are sharing resources. Right? So here's a quick example of why unwinding is important. Right? On the left here, we have a simple application that is acquiring a lock on the task list, right? And it's using that to just print out all of the tasks that are currently available. If everything works normally, right, if things are okay, here at the bottom, the task list will actually be released, the lock on the task list, right? And the reason that works is because it's effectively a scoped guard for this mutex, which implements the drop functionality. And this is, like I said, Rust's notion of destructors. So when this lock item, the locked task list, falls out of scope here at the bottom, the lock will be unlocked, right? And this is important because if it's not unlocked, everything else that needs the task list will fail, like scheduling. And then the problem is, what if we have a panic, which is Rust's version of a language level exception, right? We don't reach the bottom of the scope, right? So we need to make sure that if we do have a panic, we start the unwinding procedure to make sure that all of these resources on the tasks stack and anything else that it has acquired are released, allocations are undone, things like that. That's why it's so crucial, right? And this is actually how we implement resource revocation as well, right? So revocation is actually a well-recognized challenge, especially in the capabilities literature. Because they argue it necessitates either inefficiency due to layers of indirection on every resource access, or unsafety, which occurs from potentially unsound behavior when you may use a resource that has been invalidated unbeknownst to you, right? So we argue that Theseus can completely bypass this challenge by making sure that resource revocation only is driven by the language. And this is, in my opinion, the only way that we can do it truly safely, right? So what this means is that it only happens through the unwinder, which is okay because the unwinder supports applications, tasks, system tasks, kernel code. They're all basically the same in Theseus, right? This allows us to reuse code routines for cleanup during both normal execution and exceptional execution, like a language level panic or CPU exception or fault, right? So by default, we need to make sure the OS can still revoke and reclaim resources. And the way we do that is effectively killing a task. Now you may say, wow, that's really harsh, right? Is that too coarse-grained? And the answer is no. It's actually the only way to ensure safety, right? If you think about it, if a task that expects it's operating under the assumption and it expects its resource accesses to be valid, what happens if those resources are suddenly yanked out from underneath it? I would argue it can't ever access safely, right? And that's a problem, especially in Rust code, which was determined to be safe at compile time, right? So this is really the only way to ensure safety by intralingual revocation. Now, most of the time we can avoid killing a whole task just to reclaim resources. We just implement types in a revocation-aware fashion. For example, using options or weak references that force the program logic to explicitly handle and express the possibility that a resource is absent and that it's been revoked. Right. Okay, so I'll give some examples of this coming up, but next I want to talk about how we avoid state spill. All right. So our key technique in addressing state spill overall is a general one called opaque exportation, and it has a corollary of stateless communication. This allows us to avoid known spill hole abstractions like handles and Unix-like signals. There's also quite a lot of other details for how we address state spill in various contexts, like shared multi-client states, soft states, or hardware-required states. But just due to time constraints, I'm going to discuss those later, or we can discuss them after the presentation. Those are found in my thesis. So first up, what is opaque exportation? I see it as a direct result of intralingual design. right? Effectively, what it does is state that the responsibility of holding a progress state should shift from the server or a resource provider to the client or the resource user. And this is only possible under two conditions. One, the server can safely relinquish its state to the client. And by safely, we mean the client is unable to arbitrarily introspect or modify that state. And the second tenet is that the system has to be able to revoke client states to reclaim them on behalf of the server, right? And as I was just saying, both of these are realized by things like type and memory safety, and then the unwinder, which allows us to revoke, in the worst case, resources by killing an entire task. Right? So here we see an example of how this might work, and then comparing it to existing classic encapsulation, right? We see during interactions from client to state, right? In the classic example, the states that the client sends, for example, configuration or other states that represent its progress with the server, will be stored within the server itself, right? And those states build and change as the interactions proceed. With opaque exportation over here on the left, we see that the state is exported, obviously, back to the client, such that the client now must shoulder the burden of maintaining that state, right? The lock here represents that it can't see what is inside the state, not that it's locked in like a mutual exclusion type fashion, just that it's not visible beyond the bounds of type safety ensured naming visibility. Right? So opaque exportation allows us to avoid some classic spillful abstractions, right? Like handles and signals. In a conventional design, a handle is basically some client-side opaque data that refers to some server-owned data. And that forces the server to maintain not only the actual data, but a table that maps from that handle to the data. Think of like a virtual address or a file descriptor mapping to a virtual memory area or an underlying file. Right? In Theseus, we give the client direct ownership of that data. There's no table to maintain on the server. Likewise for signals, signals delivered, for example, in a Unix-like system from the kernel to an application process, they lack the full context of what may have happened, right? So that forces the signal receiver to rely upon existing states and context that it has acquired. Generally, those states have been previously spilled into it, so it must hold those states to handle the signal with full context. In Theseus, we use stateless communication to make sure that a message, or some kind of event that we're propagating has the full context and is self-contained, self-sufficient to be able to be handled. And we apply that to both function arguments and intertask channels, which is like IPC. So now I'm going to talk about some specific subsystems, memory and tasking, and how intralingual design and stateful freedom plays out in those subsystems. So some known problems in memory management, specifically virtual memory management, is that the action of mapping, remapping, and unmapping causes state spill into whatever subsystem entity is providing the virtual memory abstraction, like MM in Linux. It also results in unsafety due to there being a semantic gap between OS level and language level understanding of memory usage. Right? Our solution is the MappedPages abstraction, which basically allows, through opaque exportation, for tasks and clients to directly own their mappings, which avoids making any changes to the state of the memory management entity. And it also bridges the semantic gap, which in turn allows the compiler to apply its existing ownership and lifetime model and do things like borrow checking and safety checks to arbitrary memory areas beyond just the stack and the heap, which it has built-in models for. It also enables safe reinterpretive typecasting for memory regions, which is kind of like a fundamental OS feature, right? Typing untyped memory via struct overlays, right? So here's an overview of MappedPages code. In the top left, we see it's just a struct with the pages that have been allocated to it, the frames that have been allocated to it, and there's a mapping between these, but we don't know exactly what, and the flags that it's been mapped with, like read-only, execute, write-only, stuff like that. Each MappedPages struct instance represents a virtually contiguous memory region. It's not guaranteed to be physically contiguous, but it may be. And then we have the map interface, which, due to its very type signature, you can see it accepts pages and frames by value, which means that it's taking ownership of the pages and frames and then returning the pages and frames after it's modified the page tables back to the caller, right? This allows, at compile time, us to prevent either a malicious or just a clueless, uneducated user from creating invalid or duplicated mappings that would violate memory safety. And this is realized by Rust's ownership system and affine types. Moving on, MappedPages implements drop, as I showed before with the mutex guard. It's similar, right? And what this is basically custom code here that the compiler can insert anytime a MappedPages object falls out of scope and is no longer in use by anybody, right? So this guarantees that the mapped pages will never be unmapped as long as it exists, right? And that it will be auto-unmapped upon drop. And this, like I said, this is just like guard types. Right? And this is also the only way to unmap. There is no other unmap function that you can call separately, right? And that basically makes sure that the user of a MappedPages object gives up access to that memory region before we actually unmap it, right? And the only way to actually access that memory region is by reinterpreting it as another, statically known type with static size, right? We only allow the user to borrow a memory region, right? Which is effectively overlaying a size type atop that memory. We forbid taking the ownership of that struct because that would be a lossy action that loses the connection between that overlaid struct and the backing memory. And this is very crucial to make sure that we avoid use after free errors. And we see this here in the type signature, right? Self here is the MappedPages object, and this tick m, apostrophe m, is the lifetime of that MappedPages object. And we see that we return a reference to whatever struct type after we've checked that its bounds are within the size of the region, rather than an ownership, an object of just t, which would be ownership of that type struct, right? So this is crucial towards, like I said, preventing things like use after free and other page fault inducing errors. All right. Here's an example of how we could use it for safe MMIO, right? For example, here I'm constructing a memory region that corresponds to a mapping of the high precision event timer in x86. I'm obtaining the frames, which we can do through like ACPI or something. And then I allocate pages for that. And then here's where the mapping actually occurs, right? So I lose ownership here of the frames and the pages, and I take ownership of this MappedPages object, right? Then I can reinterpret it as a type of these HPET registers, right? Which have been created with the proper offsets and size here. And then I can access it just like I would any other kind of regular program variable, which is very convenient and also safe, right? There's no worries of overstepping the boundaries of this memory region. The unwinder here will prevent leakage, right? So no matter what, if the MappedPages object is allocated here, any point after, if there's a panic or some kind of failure, the unwinder will be able to release and unmap this object, right? And finally, there's no state spill into the memory subsystem because all of the state representing the existence of this mapping, including the changes in the hardware page tables, are represented by the existence of this MappedPages object. So in a nutshell, this allows us to have the compiler check various invariants, things like the bijective virtual to physical mapping that prevents extralingual sharing, bounds checking, unmapping exactly once to avoid use after free or double free, and other things like avoiding page protected violations, which my thesis goes into more detail on. Right? So in summary, MappedPages allows us to statically prevent unexpected page faults, which is really powerful, especially for developing new features or inexperienced OS developers. So now let's give a brief example of the task management and how we address state spill in there. So our goal is to avoid state spill into the task struct, which is a known problem. A lot of standard OSs have a large centralized monolithic task struct where everything is stored. We want to avoid that, right? Because every interaction effectively in a system like Linux results in state spill into the task struct when we update some task-specific variable, right? As I've already mentioned, we do this by compiler-led resource bookkeeping, blind distributed bookkeeping, which enables us to avoid storing states for cleanup and task management within the task struct. So here's a concrete example of that. On the left side, we have an excerpt of the Linux task struct, which has a whole bunch of states. And on the right side, we have Theseus task struct with some extra items. Really only these two highlighted items are actually needed. The others are here for convenience and debugging. But you can see there's a lack of things like open files and sockets, memory regions, wait queues, signal handling, IPC information, run queue information, right? And the reason is, due to opaque exportation and intralingual design, we can store the only instance of these states and the only representation of those resources being acquired on the task stack, right? We see here with files, mapped regions, wait queues, locks, even channels for IPC, anything like that. So this significantly reduces the task drift, and my thesis goes into more detail about how we can further reduce it. Another thing that I want to highlight is one of the invariants for intralingual task design, which is that task spawning has to ensure multitasking does not violate memory safety, right? And the way that we do that is by implementing task spawning and all of the task management lifecycle functions, using the same set of generic type parameters, right, which we see here. So when you spawn a task, you pass it the function and the argument, which is its entry function and the argument it will be invoked with, where there are restrictions on these types, right? So the argument has to be send, which is Rust terminology for safely transferable, movable across different thread contexts. The return type also has to be send, and the function type is one that can be executed once, accepts an argument of type A, and returns a return value of type R. Right? Now, all of these different functions, right? So after spawn, the task will enter into the task wrapper, which will then call its entry function F. And then after it executes to completion, it will jump to the task cleanup success, or if it fails and is unwound, it will jump to the task cleanup failure routine. Right? Now, all of these have the same type parameters, which makes sure that the compiler can check for us that illegal, tasks that would violate memory safety, for example, accepting references across thread boundaries, which is not safe, can be prevented and will result in compile time errors rather than random runtime page faults. Right? Now, currently, the only extralingual operation we have is context switching. That's just because I can't figure out a way to represent things like switching stack pointer registers to the language level. It just doesn't have a way to represent that. So this is one of many compiler checkable task invariants. Other ones include that we use special locks to make sure that accessing a task state doesn't result in deadlock and it won't be interrupted or preempted. And then things like task stakes are always fully released and all execution paths, including unwinding, and that any memory reachable from a task will be safely persist beyond the duration of that task. So my thesis goes into more detail there. Let me move on to how these design principles and intralingual design and stateful freedom actually help to realize evolvability and availability, which were our two top-level goals. So in a nutshell, evolution is effectively realized by swapping cells, whereas availability is realized not only by restartable tasks, but also by reloading and replacing corrupted cells. My thesis describes more information on how we realize system flexibility, but I don't have time to get into that just now. So first up is evolution, right? Live evolution is realized by cell swapping, right? So we have we start with an existing cell namespace here, right, which has 3 crates, and let's say that we want to swap out this with 2 new crates, right? We want to swap crate C with 2 new crates J and K, right? The first thing we do is we create a new empty isolated cell namespace, which allows us to load all of the new cells in isolation from the rest of the system, right? This makes sure that we don't accidentally link against old dependencies or something like that. And then the next step is to verify those dependencies, right? We want to make sure that bidirectional dependencies are verifiable. And what I mean by that is that not only do the new cells satisfy all of the dependencies from other cells onto the old cell that they're replacing, but that the other way is also true, that all of these new cells can satisfy their own dependencies by existing cells that are not being replaced, right? And this all happens before we actually make any intrusive changes into the system. So it can happen in parallel with the running system executing as normal. The first intrusive stage that actually changes existing things is to redirect dependent old cells to use the new cells, which involves updating their dependency information and actually rewriting their relocation values in each one of their text, data, and RO data sections. And we also do some other things like update all of the on-stack references to refer to the old cell, refer from the old cell to the new cell, and then transfer states. Those are details beyond the scope of this talk. but we do have to account for those. And then fourth, we remove the old cell, which in this case is crate C, and we clean up things like the symbols, publicly visible symbols that were added to this namespace, and then we add these symbols in and the crates under this namespace, right? So effectively, we've shown an example that replaces one crate with two, but there's no numerical restrictions. Right? We can replace one crate with one. We can replace one crate and then just add a completely unrelated crate that doesn't do any replacement. Any kind of arbitrary evolutionary action is supported like that. Okay, so I've already mentioned some of these things, but I just wanted to highlight how some of these evolutionary mechanisms actually are facilitated by Theseus design choices, right? So obviously runtime-persistent bounds help simplify cell swapping, right? We can ensure in the loader that we're not overlapping different cells, text sections and data sections within memory, and we don't cross a page boundary, which makes it very clean to replace individual regions of memory. There's no lack of flexibility when we're placing objects in memory, no restrictions on location or size, right? Similarly, the lack of state spill increases the number and the duration of points at which it is safe to swap a new crate, because there are fewer dependencies due to things like stateless communication, and fewer states that have hard-coded dependencies due to everything being passed into a function that it needs to work. Right, and then of course we have the cell metadata trees, which accelerate cell swapping through a variety of optimizations. For example, dependency verification boils down to a very quick search of a symbol map, which is just implemented as a QP try. Right? Yeah, so that's basically it. There's more details in the thesis if you're interested. Let me now talk about how we realize availability. All right, so clearly many classes of faults are already prevented by Rust, right? We've already talked about things. We can recover from all language level faults, like Rust level exceptions, which is called a panic in Rust, because the unwinding tables that the compiler admits are known, have a priori knowledge of where those faults could occur. Right? So to stress test our system, we actually focus on transient hardware-induced faults that occur beneath the language level, because those are the ones that are actually really hard to recover. We have a multi-stage sort of cascading approach to fault recovery in which we take increasingly intrusive operations. Right? The first stage is just to simply tolerate a fault. We clean up the task in which it occurred using unwinding, and then other tasks that may use that shared data can continue to operate properly. This effectively is fault isolation. The second stage is to restart a task, which is to respawn a new instance of a task that failed. Right? So that could be that could get over something like stack corruption. And then the third and most intrusive option is to completely reload and replace any cells that may have been corrupted with new instances. So let me first describe how we realize the notion of restartable tasks with a safe abstraction. So I already showed you our task spawning infrastructure with all those spawn and task wrapper functions. And basically here, we extend that with a new spawn function called spawn restartable. And this is useful for things like critical system tasks, like long-running loop processes like event managers. Right? So here we see the type definition, the function signature of spawn restartable. And I want to draw attention to three parts. The first one is the argument, right? Not only does it have to be thread safe, or safe to move across threads, it has to be safely duplicable, which is what the clone represents here, right? The return value doesn't really change. It still needs to be thread safe, right? The function does change. It's just a regular function, which is any kind of closure or a standard primitive function, right? That can be executed multiple times rather than a function once, which can only be executed a single time. The difference there is that a function once can capture its environment. It's a closure that can capture its environment by value, whereas this can only capture it by reference, which is important for the ownership model to ensure memory safety. Right? So these particular things altogether basically allow the compiler to prevent a restartable task from being unsound. For example, a task that accepts that captures its environment by value cannot be created as a restartable task, and that will result in a compiler error. The next stage is reloading corrupted cells, right? So this is kind of our last-ditch effort. It's effectively the simplest possible case of cell swapping, right? You're swapping a crate with itself, right? So imagine here, crate A, we have some hardware error that results in, for example, memory corruption in one of its sections. The way that we get around that is to, as you saw before, load a new instance of that crate and then swap it with the existing crate, such as dependencies are rewritten and this is removed from the namespace. Right? And then we can go ahead and restart a task that may have failed, and it will run atop and run through these new crate sections here, such that the corruption is no longer there. So this addresses, corruption due to transit memory errors or something like that in text or RO data sections in a particular cell. So another thing I want to highlight about fault recovery is that it works in the core of the operating system, right? There's no real limitations. You only really need the ability to have a basic execution environment that works, where we can access the stack and just call functions. It's really that simple, right? So we can have many subsystems fail before we've been unable to recover. In comparison, microkernels and other fault-tolerant systems have a larger set of dependencies for their fault recovery approaches to work. For example, if something fails in a microkernel, you need user space to work, you need to be able to switch between context and address spaces, you need to be able to have interrupts to do so, and IPC to communicate between the user space server entities. So that allows Theseus fault recovery to be more arbitrary. Okay, so you can find more information in the thesis, in the thesis. But now I want to talk about some of the evaluation work that we've done. Right? So the evaluation is in 4 parts. First, we talk about live evolution case studies. Then we talk about some fault recovery case studies. Then I want to highlight some of the costs of choosing intralingual or spill-free designs, performance costs. And then we have a kind of a general micro-benchmark level comparison with existing systems like Linux. So first up is live evolution. So in my thesis, I have several cases of this, but I'm just going to present 2 here. Right? The first one is evolving our IPC layer, which is effectively inter-task communication, from a synchronous rendezvous-based protocol, which is bufferless, to an asynchronous buffered IPC protocol. Right? So we advance the state of the art here beyond existing monolithic microkernel OSes by allowing, in this case, safe joint evolution of user-kernel interfaces. Right? The inter-task or inter-process communication level must be in the microkernel or the monolithic kernel. There's no way to avoid that, right? And that means that if you want to change it, you have to jointly evolve not only core components that may exist in the microkernel, but that interface from user space to kernel space, right? Now, the question is, do microkernels actually need to change? This is some feedback that we got from a reviewer in one of my previous paper submissions. And they were arguing that microkernels are so simple that they don't need to change. So I actually went through all of the change histories of major microkernels like Minix and SAL4 and found that IPC is actually one of the most noteworthy types of evolution that occurs, right? So they're changing from, in this case, synchronous to asynchronous. That's why we chose this particular case study. Right? So I want to bring your attention to this diagram here in the bottom right, which is effectively a timeline of the procedures that have to take place, right? I already described these in the stages of realizing evolution, but I want to highlight a couple of things, right? Is that 2 stages here are what I call critical stages, where the system may need to be paused such that we do things like rewrite relocations and dependencies atomically, right? Now, this is not always the case, but sometimes we do need, depending on the nature of the component being evolved, we may need to pause the system, right? But that downtime is in general very, very short. We're talking on the order of a few hundred milliseconds at the very most, right? The other stages, like I said, are non-intrusive and they can happen in parallel with a regular system execution, right? So the noteworthy thing to mention here is that Theseus doesn't lose any state when evolving from a synchronous to an asynchronous implementation. Simply because we can evolve the entities themselves independently from the execution context. So our second case study evolves the existing round-robin scheduler into a priority scheduler, right? Now you may say, oh, this is really trivial. Every system can do this, right? Well, the major distinction is that those systems have a priori support for multiple scheduler alternatives, right? And they require a common interface. Theseus does not. In this case, we booted Theseus with a system, a very simple a very simple round-robin based scheduler that didn't have any kind of notion of the potential for multiple scheduler policies, right? So what this shows is that we can change the modularity of the OS itself, right? The bounds of the entities, because for example, the priority scheduler also requires other components to be evolved simultaneously. For example, the run queue management from a round robin, like a double in a queue based run queue to something like a binary heap based run queue. Right? And it also shows that we can evolve core entities that are used incessantly and also are at the center of the dependency spider web within the core of the system. Right? So there are a lot more examples in my thesis, but since I'm short on time, I'm going to go ahead and move on. So now I want to describe some of our investigation into how well Theseus recovers from hardware level faults. Right? So let me just briefly describe our fault injection methods. Right? So we wanted to be able to automate arbitrary changes to hardware state. Thus, we run Theseus atop QEMU, which is a popular processor emulator. And we do things like randomly flip 1 bit in memory, or change the whole 64-bit chunk of memory, or randomly increment an instruction pointer to skip instructions. Now, these techniques are widely used in other fault tolerance literature. We didn't come up with them ourselves, and we try to adhere to the standard practice there. Right, so the goal is to stress test whether or not Theseus can recover from transient hardware-induced faults beneath the language. As I already said, language-level faults are guaranteed to be recoverable. Right? So in general, one of our general experiments find that out of 800,000 faults we injected, there were 665 that manifested in actual errors in Theseus. Right? And we inject these faults while running workloads that stress core components like graphical rendering, spawning tasks, accessing file system contents, and sending message over inter-task communication channels. To make sure that our faults actually hit more often and manifest as real observable problems, we target fault injection into the working set of memory, things like the task stack, its heap sections, and its sections in the cells that it uses. Right? So we find that in general, we can recover from just under 70% of faults, right? In 10% of the recoveries, roughly 11%, we could recover simply by respawning a new instance of the task through the restartable task abstraction, which indicates that the corruption occurred in the task stack. And in the other 90-ish% of cases, we had to reload the cell, which indicates corruption in a text section or something like that. Now, we do have some failures, and this is due to primarily a lack of what's called asynchronous unwinding, which means that whenever an exception occurred, whenever the fault actually manifested, that point of failure, the instruction pointer, wasn't covered by the compiler's unwinding table, which means that we weren't able to completely unwind it, right? Which sometimes results in things like a hung task, because some of the things that we want to unwind could be a lock that needs to be released. So we're working on various ways to circumvent that, but those details are in my thesis. We also want to show that we can recover from microkernel-level faults that a system like Minix cannot, right? So as I mentioned before, microkernels can recover from faults in user space, but not within the microkernel itself, right? So what we did here is we did a painstaking manual inspection and of both Minix's IPC layer and Theseus's ITC layer, and created a series of reproducible deterministic faults. Out of the 13 faults in those subsystems we were able to create, Theseus recovers from 11 of them, right? In the other 2 cases, we had a hung sender or a receiver task, which could be solvable by complementary approaches like watchdog timers that reset the channel. Minix actually failed to recover in all cases, and it crashed in all but 2 of them. In those 2 cases, it loses a single message and then proceeds to receive other messages. But because microkernels expect IPC to be lossless and always successful, this is a problem for proper functionality of the user space servers. So now I want to briefly touch on the cost of intralingual and spill-free design. There are quite a few examples in the paper, but I'm just going to discuss 2 here. The first one is, what is the cost of MappedPages? We actually find that it performs better than a conventional approach that would use something like a red-black tree to link up a virtual address handle to the underlying VMA data structure, right, virtual memory area. And this is because Theseus represents memory regions using MappedPages, which are distributed into the tasks that directly own them. So there's no need to search like a central tree or a per address space tree or updated that holds the VMAs. Now, I don't think the performance improvement here is hugely significant, but it just shows that state spill-free and intralingual designs aren't always worse. But in some examples, they are, like in the case of intralingually implementing a heap, right? So this is not to introduce new heap designs or anything. We are using a standard per core heap that exists within that single Rust global alloc example. And basically there are multiple examples and multiple instances of the heaps, and they share lists of memory represented by MappedPages. Right? Now the unsafe design uses things like raw pointers, and it loses the language context that relates an allocated chunk back to that underlying MappedPages object. But the safe design does not lose that. It preserves that by using, like a collections data structure, like an intrusive tree or something, to make sure that we don't lose that lifetime relationship. And we see that this can cause up to 22% overhead in certain tests here. Right? So here we ported the thread test and SH bench heap benchmarks to Theseus. And we see that the worst case here is up to 22% overhead, comparing safe to fully unsafe. So there sometimes can be cost to intralingual design, but in this case, we haven't really noticed a significant impact on larger application runtimes. So finally, just to do a brief comparison against an existing OS, we re-implement some existing micro benchmarks from the LM bench suite, and we re-implemented them in safe Rust. And we tried our best to give Linux the advantage to make it appear better than Theseus. But in general, we find that performance is as expected, right? I'm not trying to claim that Theseus has better performance than Linux overall. We need more macro benchmarks to really make that claim, and that's something that we're investigating actually. But you can see that in general, core micro benchmarks are relatively faster, 2 to 3 times faster in most cases, due to the lack of having to switch between address spaces or privilege modes, and this is to be expected. Right. So there are a lot more details in the thesis, but since I'm running low on time, I'm going to just briefly touch on limitations and then I'll conclude. Right. So there are quite a few limitations that we have. Of course, I would say one of the most significant ones is actually here at the bottom. Everything needs to be written in safe Rust. Right. There are some approaches that we can take to avoid this. For example, implementing other safe language runtimes within safe Rust, which has actually been done for things like Java. And I've even seen some isolated runtimes written in Rust to support Python. Another problem we have is the necessary evil of unsafety, right? And I go into a lot of detail in this in my thesis, but effectively we want to differentiate between 2 types of unsafe code. Infectious code, which can violate isolation, both data isolation and fault isolation, and then innocuous code, which can't, right? So we have some compiler tools that run as plugins during the Rust compilation process to detect this code and try to throw a compiler error if we find it, right? As I mentioned before, we also have the issue of lack of asynchronous unwinding support in Rust, which can sometimes lead to incomplete fault recovery. And we're working on augmenting the synchronous unwinding information with a variety of different other OS details like cell metadata and debug information. Sorry, they're watching my window right now. So finally, let me wrap up here. So in conclusion, the design of Theseus comprises a structure of many tiny cells that are all dynamically loaded and linked such that they have runtime persistent bounds. We empower the language and leverage the strength of the compiler to the fullest extent possible through intralingual design, which goes beyond safety to shift the responsibilities of things like OS resource bookkeeping into the compiler itself, which then allows us to avoid state spill in cooperation with several other techniques. And overall, this is designed to facilitate evolvability and availability, right? But those are not our only 2 goals necessarily, just the one we present here. Just to give you an idea of the current status of Theseus, I've been working on it for almost exactly 3 years now. We've had quite a lot of collaborator churn, but despite that, we have seen effective contributions even from beginners. People like, we've had almost completely inexperienced freshman students come in and write things like a terminal, which is relatively difficult to implement properly. So I'm really proud of the, I think, approachable environment that Theseus offers towards OS development. We support most standard OS features on both x86 desktop and server PCs. We've tested on a variety of desktops and one server rack with 72 cores. That includes things like preemptive multitasking, multi-core support for SIMD, APIC, ACPI, all of those things. We did have some delays, right, which is why I'm here so late, finally defending, with some features that didn't actually pan out. For example, I spent several months implementing user space and system call support before we realized that we could leverage the power of Rust by ditching those and transcending that reliance on hardware provided isolation. Another really cool project that I spent quite a few months on was implementing a SIMD personality, so we can run SIMD-enabled code along non-SIMD-enabled code to get the best of both worlds within the same execution environment, which is really promising for things like baseband processing on edge nodes. But that's also part of future work. In the immediate term, I want to expand our support for legacy compatibility by fully supporting the Rust standard library, which would allow us to run many existing crates off the shelf. And as long as they're safe, we can do that without any kind of concerns. We're also using Theseus as the basis for reevaluating whether or not safe language OSs actually have performance benefits. Are they more efficient than hardware protection? Right? And then finally, I want to open source it and hopefully get some users. That would be nice. So yeah, before I wrap up here, I just want to acknowledge some folks who have gone a long way to helping me out in this journey. Obviously, I have to thank my advisor, Lynn, here on the left, who has provided, I would say, quite a lot of the research focus and refocusing my wild and crazy thoughts into something that's actually tenable. And then on the top here, we have Namatha, who has helped me quite a bit with the fault tolerance work, and Ramla, who has helped with a myriad of things, from performance evaluations to implementing some networking support, as well as exploring the SIMD personality with me. And then Min Hong down here, who has already graduated and is now working at Google, but has helped me just talk through algorithms and things like that. And then Win Cho down here on the bottom right, who has helped me with display and graphical processing. So that's all I have. Thank you so much for listening, and I'd be happy to take any and all questions.
Thank you, Kevin. Thank you.
Hope I didn't run too long. Just looks like we're.
I think you're fine. You're fine. I was going to. I think we're 12 minutes past 1 hour. So
yeah.
I think now it's open questions. Anybody can ask questions. Then we'll have a closed door session. Only committee member asks questions.
Sure. I have dozens of backup slides, so feel free to get technical.
Don't tell us. Okay. All right. Don't. I'm kidding. Dan, do you have any question to ask right now? Eduardo?
Yeah, I'll ask a question. First of all, I think this is very interesting work.
Thank you.
Congratulations on a good job.
Thank you.
I do have a question in terms of global resource management. For instance, if we were to allocate the memory allocator, for instance, or other types of global resources, who would be maintaining that state?
Right. So that is actually something that I discuss in one of the sections in my limitations section in the thesis. So basically, we want to make sure that when an application or a task acquires some resource, it doesn't have to worry about any other application or anybody gaining access to that resource, right? So by default, things are not shared or tracked centrally in any particular place. But for some things, for example, like adding in functionality for demand paging, right? We would need to keep additional centralized state like that. And I think the way to do that is via weak references, right? Such that, for example, if we have something like demand paging and we want to figure out whether or not a page fault can be satisfied for like a file system or something, we can look at that central, not repository, but central list of weak references for mapped pages to be, and then use those to satisfy, the needs for demand paging. But in general, there isn't like a central, repository of all system-wide states. So if you wanted to do something, another related category could be like just tracking all memory usage, right? then you could, optionally store a list of weak reference to all of the MappedPages objects, such that, we're not causing state spill and we're not violating the sole ownership that the applications have over those MappedPages objects, but we still have the ability to then kind of, summarize them for statistical purposes or something like that. But yeah, by default, that's not something that's in there for a general OS resource. If you want it, you can add it.
I see. So if someone calls, if a process allocates memory and then finishes, I was just wondering whether that would cause fragmentation.
If a process allocates memory and then what?
If memory is freed, for instance.
Mm-hmm.
So how would you keep track of the freed resources if it's not kept global?
You're talking about like a page allocator and a frame allocator, that kind of. Right. Yeah. So I mean, there is no way to avoid state spill in allocators, and I actually have a slide about this for the heap because it's a similar issue, right? Effectively, while it is technically state spill, like the action of allocating something, like allocating a range of pages, right? We need to make sure that another allocation request doesn't, re-provide the same pages, right? However, it's actually not necessary to consider that state spill specifically within the allocator. And the reason is those states are represented by the returned object types, for example, allocated pages or allocated frames, right? So it's sufficient to track the propagation and movement of those owned objects to do things like resource management to make sure that we're cleaning up and dropping and freeing allocated pages or frames. But yes, in general, an allocator is going to represent some sort of state that needs to be held. There isn't really a way to avoid that, right? But we represent it with those owned types.
I see. So does the current OS have a file system?
We have a very basic file system support. It's not something that I really focused on too much. We have full in-memory file systems. We have basic support for a FAT32, but it's very trivial. There isn't a lot of like great support for caching and stuff. Yeah.
Okay. So I guess my question is, right, when you interact with peripheral devices such as the disk, there may be multiple layers that need to operate together. Some of the optimizations need to cross the boundaries of the modules, like the cache layer.
Right.
Right.
Go ahead. Yeah.
So I was wondering whether this would fundamentally limit this cross-module optimization that you would typically need in like block cache layer and others.
Yeah, so I actually have tried to implement a block cache specifically for ATA storage devices, just the disks, not at the file system layer. And I haven't found it to be significantly limiting. I think maybe it's a little bit less ergonomic than what you might find in a system like Linux, like within the kernel, simply because, well, I would say in general, Rust is more of a stickler than C, right? Of course. So I don't think it's limiting in like a functionality sense, but, for example, you do have to construct like a series of type wrappers, for example, like you create a storage device and then you wrap it in perhaps like a buffered reader and then maybe other layers of caching. So I don't know for sure that there's no limitations there. I think that's something that I would have to discover, as we flesh out the file system caching layer itself, because there could be, I can envision some problems there. But specifically for ATA storage devices, I haven't encountered any limitation there. It's just you have to be cognizant of it as a implementer.
Right. So I guess I'm not primarily concerned about functionality, whether it could be implemented, but the performance optimizations. Right. Sometimes you would want a centralized cache, for instance, the block cache, so that everybody has the same view of what is cached and what is modified. If you don't have a centralized view of the block cache, right, I was wondering whether that makes some optimizations difficult.
Yeah, we actually do have a centralized block cache, and I mean that does represent an example of state spill, right? There's no way to avoid that. I don't know that are you asking whether or not the fact that it's centralized causes potential performance problems? Or
no. So I was thinking if it is fully decentralized, even to the cache layer, right, then it seems difficult to maintain a coherent view of what is cached.
Yeah, you would be right. In the way that I've implemented it so far for the storage devices, it is central, right? And that does represent a form of state spill. But I would note that in most of the cases, like most of the time, unless you're doing something like you have a dirty page that still needs to be written, that's really the only dangerous case of state spill, because all of the other cached pages could be reclaimable at any point, and they're idempotently, recreatable. I have, I do have slides on this as well, but I don't know where they are. So many things. Yeah, I don't have slides specifically on the storage device, because that's sort of like a peripheral concern beyond like core memory and tasking. But yeah, I agree. You know, I think there could be some performance restrictions there based on things like contention, right? If we're having to repeatedly lock or insert or remove things from a giant list of a centralized list of caching, I could see that being a problem. In a lot of cases, I found that we can avoid contention as long as we're not requiring mutability. So, for example, if we had like a write through cache, I don't think there's any kind of stateful concerns, but a write back cache maybe would cause problems performance-wise due to contention. Yeah, I'd have to investigate that more.
Okay, thanks.
Sure. Yeah, thank you for the question.
So I was wondering if you could speak to some of these recent memory attacks that we've seen, speculative execution.
Oh yeah.
There's a whole large family of them, Spectre, Meltdown, and many, many more. And it seems that some of your attention to state spill might somehow be relevant to that. And I'm wondering if you could speak to that.
We have actually, yeah. So in the broader sense, we have actually we've tried to really understand and explore the relationship between state spill and security. One potential issue that we identified was not along the lines of like speculative execution, but it is sort of related, TOCTO attacks, right? Time of check to time of use. We believe that if you have a state spill free system, or at least a given interaction, right, you wouldn't be able to actually construct and exploit a TOCTO attack. But I'm not necessarily, so that's at the software layer. I'm not necessarily sure that that would apply down at the hardware layer, right? There's nothing in Theseus that we're doing to specifically mitigate the speculative execution attacks. All I will say is that I have personally, correct me if I'm wrong, I have yet to see an attack that can be constructed in purely safe code. Maybe those attacks will surface in the future, but all of the attacks I've seen wouldn't be doable by, for example, an application code in safe Rust. But in terms of OS level support for mitigating it, there's nothing really there, because we're not switching between multiple page tables, so there's nothing to leak in that sense, right? We're relying purely on language level safety and our unwinding based fault isolation to make sure that we're not exposing secret confidential information. That's all I can really say about that.
Okay, so another question. You made an early engineering decision in the system to have a single unified heap.
Yeah.
And in the history of people playing with language-based operating systems, we've seen a number of variations where people have multiple heaps, where a heap corresponds roughly to a process.
Mm-hmm.
So that way it's easier to know everything being used and you can kill it all. But then, of course, anything you pass back and forth gets complicated. You end up with shared heaps and private heaps. And so
Yep.
I'm just curious, how far did you even wander down that road before rejecting it? And what's your opinion on on why a shared heap?
Yeah, we've actually had that conversation many times, right? So I should clarify that the heap, we can implement arbitrary numbers of heaps, right? What is important is that there is a single concept of an allocator instance, right? So all allocation and deallocation system-wide goes through this single interface, but there can be multiple heaps. For example, our current configuration is a per core heap, right? Which is actually something that's tricky to do in existing systems that don't have this kind of single view of virtual addresses, right? But that's mostly to reduce contention on having one single system-wide heap instance, right? We actually do have multiple per core heaps. So the other part of your question was about did we investigate like per task heaps? Yeah, we can do that too. The reason I don't necessarily want to do that is because tasks are fairly lightweight so far. If a task wanted to create its own heap, it could. There's nothing stopping it, but it still needs to be created within the bounds of that single intralingually implemented heap interface, right? So yeah, like I said, per-core heaps mostly there to avoid contention. What else? Right, so systems like Singularity, they have this problem of sharing, something that one process allocated on the heap with another process, and they have something called an exchange heap to mitigate this, right? Where you have to explicitly transfer, like the programmer needs to explicitly transfer something from one SIP, which is Singularity's software isolated process, to another, right? I didn't want to deal with that in Theseus, mainly because everything, you can visualize everything as being built and seen by a single invocation of the compiler. So it's really difficult to express that intralingually, right? Rust expects, the compiler expects a single heap instance, right? So the best we can do, or I think also the safest option, right, to avoid all the difficulty of doing exchange heaps and moving state between heaps, is to just have that single global view of all heaps, even though they are divvied up according to whatever arbitrary notion you want, like per core. Yeah, that was my decision. But I think the good thing is we can change it, right? We can arbitrarily create in heaps, but I don't believe there's going to be a change in like the overall structure of this, multiple heaps within a single allocator. If that makes sense.
So one last question, and then I'll let some other people go.
Sure.
The Talk OS from Stanford
Yes.
is also built in Rust.
Yes.
And they have a notion of a Rust kernel with processes hanging out that could be written in any language.
Right.
And then, of course, you can't make any guarantees about something that was written in C, but you can make guarantees about things that are written in Rust. And they do it all with a goofy embedded processor. So they have segments, not real virtual address spaces.
Right, right. They use the MPU, memory protection unit, for like memory grants that the user space process can create. Sorry to interrupt.
So it sounds like what you're doing is comparable to what they're doing for the inside part. And I'm curious if you've thought about building an outside part, or if you want to talk about differences and similarities.
Yeah, you're definitely right. So I wouldn't even consider Talk necessarily a language protected OS, right? They do use hardware memory protection, just like Redux, which is another Rust, another Unix-like OS re-implemented in Rust, right? The safety extends to basically just in kernel units, right? So Talk also has like a whole core of unsafe code where they basically say, anything within here is trusted, right? And we see this a lot in safe language operating systems, right? Singularity is the same way with things beneath the C# level. But yeah, I mean, I definitely agree with your characterization of that. We could, basically take Theseus and it could serve as kind of like almost a unikernel for Rust, right? You can run multiple Rust applications there. It's effectively, a safe runtime for Rust that kind of does away with all of the platform-specific ambiguities, and when those are required, it implements them intralingual. Right? So if you look at something like Talk, there is a semantic gap between a user space application, right, and an underlying Rust code in the kernel, and then there's even a gap between their safe level of Rust, which is like drivers and such, and the core kernel. That's an implementation. I'm not hating on them, not to bash them or anything. I think that system is very powerful. But yeah, it's a different goal. Here we're trying to do everything, utilize the language protection power as much as possible. And I think they utilized it at a moderate level, but it can go further. Yeah.
Okay.
Any further questions?
Yeah.
Yes.
Go ahead, Eduardo. Go ahead.
Yeah. So first of all, congratulations for this work, Kevin. I think it's very commendable that you decided to take the bold route of, what I want to prove this hypothesis. So I will build a whole OS from scratch.
Maybe a bit full.
So kudos to Lean for supporting you and doing this as well. So
yes,
I think it will pay off when you start releasing it in open source. I have a few questions. So what will happen if you have hardware that has a state, and you may spill state into hardware just because of its design. So like things like the GPU, for example.
Yeah, that's a great question. So I can answer that with a kind of a comparative example, which is if you think about the MMU being sort of an accelerator like the GPU, not that it is, but it has its state, right, in the form of page tables and TLB cache entries, right? We actually don't consider these to be state spill. We do consider them to be side effects that are externalized to hardware, right? What's important is that you mirror the change in hardware state with a corresponding software state. So that is exactly what MappedPages does, right? There has been a change in state to the MM entity, but it's not represented as a program state. It's represented as a change in page tables and maybe some TLB entries that have been brought in. And the very existence of that MappedPages object that's owned by the client task, that represents that change in state. So we know by virtue of that existing, there has been, some change to these page table entries and, potentially these TLB entries. And that's exactly what we use when we're remapping and unmapping a particular MappedPages region. So to answer your question, segue back into the GPU, my larger goal is to implement kind of like not really a capture, but like a container that kind of summarizes the state of a device, and then it can be owned by and exported to the client, right? I don't know how easily that would be done for a very complicated device like the GPU. That I found in most of my previous work, like before Theseus, the GPU was often the exception rather than the rule. So I don't know for sure, but it does work for things like storage devices, right? We can have a client-side software state that fully represents the state of, a disk or something, right?
So if you need to unwind like a hard drive state, like you will undo the hard drive state as well, or how do you unwind something that had like a side effect?
Yeah, that's a great question. That depends greatly on the nature and the semantics of the resource, right? So you can have, something I actually do is I create like multiple wrapper types around other types. And each one of these layers, right, when it's dropped, it'll recursively drop and clean up the inner components, right? So if you want to layer additional functionality, like undoing something, if you want to, I don't know, maybe you have like some kind of hardware transactional memory that you want to support, right? Or rather, something transactional that you need to undo, right? That is where you could implement it. You could implement it in a drop handler that the unwinder could then run. But we don't necessarily want to do that for all cases in the whole system, right? I mean, you don't necessarily want to undo all operations that occurred on a disk drive, right? Maybe just the ones that are, in flight. You issue some cancellation routine, right? So unwinding can run any kind of arbitrary logic, and it's just based on whatever you put into those drop handlers. Yeah. So in most cases, the drop handlers are actually relatively simple. But in some other cases, like for example, in the case of a task, right, dropping a task means that the task is now exited, it's done. There's a little bit more complexity that has to go in there to make sure that we clean up all of the task states. And I imagine, if we wanted to undo something like for a hardware device, we would need a little bit of complexity there. I've actually been thinking about this in depth with the NIC, right, the network interface card. We have a E1000 driver. And I want to be able to mirror the state of that device in some way in a software state such that we can reset it to like a known state when it's dropped, for example, right? We've also done something similar for the performance monitoring unit in x86, where we have basically a set of counters, and we have an abstract type that represents each counter. And basically when you drop that, it makes sure that the counter is reset and returned to 0 and marked as available, not in use, right? So that's the kind of thing that we can do with drop handlers. And unwinding will make sure that those run even if you panic while doing something like performance monitoring.
Right. And also on terms of kind of like security, like since you have like a single address space, is there any risk for like, in ROS you can have like uninitialized memory, right? So could like a malicious driver like keep like having uninitialized memory trying to snoop into like maybe some area that other component allocated and eventually freed, or is everything free scrubbed?
Yeah, I mean, that's a good point. So in general, in Safe Rust, you cannot have uninitialized memory like that, right? So that's
Awesome.
why, yeah, that's why we have all of these different rules to kind of merge the concept of memory with, or Rust concept of memory, unify it with the OS's view of memory. To answer your question, I mean, you could do it with unsafe code, right? That's exactly the point behind looking at, here, actually, let me bring up this slide. That's exactly the point behind looking at unsafe code, right? So what you're describing is what I would, what I termed infectious code, right? It's stuff that can violate isolation, right? So in general, we want to prevent this, and we've done some work on a compiler plugin to run and check unsafe code for this, and it's basically it's essentially based on whether or not the code the data that is accessed by a given piece of code would also be fully reachable from only safe code. Right? So if it's something that you can do in safe code but just requires unsafe code because of Rust or because of hardware, it's generally innocuous. But what you're describing sounds like something that would be infectious, and it would be our goal to throw a compiler error if we detected such behavior. Did that answer the question? Or I can go
So
on.
I think we still have two audience members here. So do you have questions? If you guys don't have a question, we'll go to the closed door session right now.
I have a question.
Go ahead, Maximally.
So I'm thinking about the future of the Theseus or the use case. So because Theseus is very good at set spill free and isolation, and I think that Theseus can be used for containers like Docker. So my question is, have you thought of that direction? Or if so, what is the missing part in Theseus for now?
I haven't specifically thought of that, but I often view, like in my mind, I view the Theseus architecture as kind of like just a unikernel-like runtime for Rust, right? So, you know, as where you may have like some very simple, have you heard of include OS, right? It's that project that basically says, you know, you just write a simple C main function, you include this header, and then it can run on bare metal, right? That's almost how you can view Theseus, especially if you strip away some of the unnecessary functionality. So I think it could comfortably sit within a VM or perhaps a container to provide a high level of safety within a container. But I get the sense that you're asking about whether or not you could realize containers atop Theseus, which would effectively make it a virtual machine of sorts, right? Or at least a process virtualization. That's what you're asking about, right?
Yes, and one of the reasons I'm thinking about container is the feature of multi-personality of Theseus.
Oh, right. Yeah, I didn't get into that, but effectively, yeah, I mean, you can think of each cell namespace as being a container. And I actually use them to create sort of a process abstraction where you have multiple like libraries or applications that are all linked together and can see each other, much like multiple tasks within a process, right? Let me pull up the, right. So we have this notion of cell namespaces, and I didn't discuss flexibility, but it's in the thesis. And basically it allows you to, you know, just vary one or more arbitrary crates. For example, here I've replaced crate C with crate X, right? Which could offer a slightly different variant of functionality. And that's how we realize personalities. So if you want to consider each one of these as being a container, you very well could, because they do, basically we do think of tasks as running in or within a given namespace, just because they're linked, their entry function is linked against the particular code in a cell namespace. Right. So to that sense, we could provide containers. I'm not sure how they would compare against, you know, the more strict like file system jail siege root style containers that you see being used in like LXC Linux containers, or I assume Docker is built on that. Yeah. I don't know. I think this is like a light form of containers, right? You could argue that.
You know, your Microsoft internship project is about the container. So
right. Yeah. I'm about to go talk to Microsoft about containers. I really don't know too much about them, so maybe I'll have a better answer for you in a few months. But
okay.
Yeah, I do think cell namespaces could serve as a basis for containers.
Last call for audience question. All right. Okay. So thank you for attending Kevin's defense. So if you're not a committee member, please leave the room.
Thank you guys very much. Appreciate it.
Thank you, Ramla. All right. Now I think it's only the committee member here. So this is now we're in this closed door session. No, I think Jacob, you need to leave. Thank you. Now we're getting to the closed door session for the committee members. Thank you. All right.
Sure. Yeah, I can remove them. Okay.
All right. Okay. Guys, go ahead. Fire. Dan is
welcome in the future too.
That's really
Later.
I have a few more questions, like kind of like just like things bouncing off my head. So
Yeah,
I was thinking, like thinking of like work I have done in code overflow. I was thinking, this may like maybe like something you can apply to, like, for example, saving power or improving performance. I imagine like most of like smartphones now that have like multiple cores, like a weak core for like things like just managing Wi-Fi, stuff like that, and like the main core that is more powerful, right?
Right.
Do you think you can use Theseus to offload from the weak core to the powerful core, or vice versa, in tasks at the OS level?
Yeah, I actually think that the personalities I just showed would be a perfect example for that, right? So I have a similar example using personalities to realize different scheduler policies on each core, right? Again, like the live evolution example, without having some kind of dedicated infrastructure for that, right? You simply link, well, that requires you to pin a task to a core, but assuming they are, right? You simply link a task to a particular scheduler implementation, and then it, within that cell namespace, it will use priority or whatever, right? So you could have something like that where you have different cell namespaces for a weak core versus a strong core, like a big little ARM architecture. That's the kind of thing you're talking about, right?
Yes, exactly.
Yeah, I haven't thought about how that could save power, but I'm aware of, at least in Linux, there are some power over energy aware scheduler policies. So I feel like that could be pretty quickly prototyped with it.
You're just thinking about like you're running your normal core and maybe like something because of like in previous data, you realize that actually it's cheaper to offload and you can still leave it with the same performance in a lower core. And you can automatically adapt your OS. So like you can build like the same OS for like a new phone and the same for an old phone. And depending on the phone's capabilities, it will, this same model will run in the fast core or in the slow core, depending on the hardware.
Yeah, definitely. I don't necessarily think that requires cell namespaces to run, but it may be a good, convenient, and easy way to structure them in a way that makes sense to the developer who's setting up one of those namespaces.
And how will be like the minimum unit that you could see like being migrated, like a task, or you will think of like a user space process, or both?
Yeah, so there is no concept of user space processes currently in Theseus. So it would have to be a task, right? That's the only concept of an execution context that we currently have. I have actually compared, in my thesis, I compare the structure of Theseus to like microservices and then serverless cloud, like functions as a service providers, right? And I think that there could be a lot of, there's a lot of interesting overlap there. Like even though we weren't inspired by them, there's similarities in structure. So we could potentially do something like run one function in a particular context, like a cell namespace or something. We sort of did this with our different namespaces for SIMD and then
Right.
but it's not exactly the same thing, but it's similar in that those two worlds, those two personalities were built with completely different invocations in the compiler with different compiler configuration. And using some special compiler options, we can make sure they're compatible. So I don't really know that your example would be directly related to that. It's actually probably a little simpler, but I haven't really considered how we could, I don't know, save energy or something by offloading tasks to proper cores. But I think at a base minimum, it would be offloaded at the task granularity.
Right.
Yeah.
So a follow-up like from your response. So then how do third-party applications work if you don't have user space? So like everything runs together, or how do like applications work in Theseus?
Right. So an application is effectively the same as any kind of kernel cell, right? The way it typically works is, let's say you have one application cell and it relies on 2 library cells, for example, right? The application will, like someone will type, cat or ls or something into the terminal. I'll search for a matching object file. I will load it dynamically and link it. And then during the linking phase, there will be missing dependencies, which will be satisfied by those libraries, right? So then I'll load those into the same crate namespace, right? And then they exist within cell namespace. They exist within that single namespace. And if you wanted to run another instance of that same application at the same time, you can load it into a new cell namespace, right? So cell namespaces are what provide kind of like a process or a container-like abstraction where you have everything, like in terms of visibility, right? It's a true namespace, right? So you'd have symbols from that task and that application and its library is all visible in that namespace. And then you have the same thing for perhaps a separate instance of the same application, right? And because namespaces can be recursive, right, we can build arbitrary levels. So for example, we could have one underlying kernel cell namespace for like kernel designated cells. And then on top of that, we could have one for library designated cells, right? Or if you wanted to have 2 versions, you could have 2 for separate library instances. And then you can have up to 1 cell namespace per application, right? It kind of depends on the nature of the application. For example, right now, if I want to spawn a new terminal, a new shell, I'll spawn it in a separate cell namespace, right? I'll create a new cell namespace and then load and link it into that. And what this allows us to do is like run, duplicate applications while still having visibility within each, process-like container. So that's how we do that.
Okay, so then everything is same address space and everything is on ring 0.
That's correct, right? So it relies on language safety to make sure that so for example, I think the crux of language safety is you can't access what you can't name, right? It's kind of like light capabilities, right? So in this case, you cannot name something in a sibling cell namespace, right? You can't access that. So for example, if there were 2 instances of like the shell application, for example, and they're in separate namespaces, those are completely independent entities and they can't see each other. Right? Does that make sense? Or
yeah.
Did I answer your question? Yeah. There's a lot of detail about how cell namespaces can be built recursively, and that is the default, and then also in terms of flexibility. But I can certainly expound upon that in the thesis more if you felt like it was lacking.
Yeah, when I was like looking at it, I didn't get like that part of like the applications and a lack of user space. So yeah,
okay. Great. I will make a note of that to add that into the thesis. Yeah, I'm actually really am proud of that detail, but I wasn't sure, how interesting it would be to other folks. Okay. Yeah. Thanks for the feedback.
Here's a question. I was wondering if you could speak about the future. I mean, like, I don't know if you're going to continue working on Theseus, but let's pretend that, we gave you a team of 10 talented crack engineers to work on the problem. Where would you go with this? What are some of the next interesting steps and destinations? If only you just had this crack team at your disposal.
Kevin, be careful of answer because Dan might write you a check for that.
That's actually a great question. So to answer your first sub-question, I am actually going to continue working on Theseus. I'm going to take a quick break at Microsoft over the summer, but then I'm going to continue working with Lynn as a research engineer. So I definitely don't want my baby to die. But yeah, to answer your question, like I mentioned, the first thing is to support more legacy-oriented applications, right? That involves adding support for like the Rust standard library in full. And then what you could do there is a huge library of things being re-implemented in Rust. So at a bare minimum, we would have all of that at our disposal, right? So that'll take certainly some effort. I think another significant step forward could be revisiting, just for legacy purposes, revisiting the introduction of user space, right? And hardware protection. It's not something that I'm super keen on from a research perspective, but from a practicality perspective, right? It makes sense. I don't think that it's necessarily required, but I have heard quite a few arguments, at least from other folks in the OS research world, that they're not really convinced that language safety is super useful. For example, we have spoken with Galen Hunt from Microsoft Research. He was one of the leads behind the Singularity project. And even he admitted that basically they couldn't get Microsoft to really adopt language isolated systems in full. Now that doesn't mean it's totally useless, right? Still having some level of strong bounds and isolation just within the kernel itself is very valuable, even if it doesn't extend to the applications in an intralingual fashion. Another thing that I wanted to look at was actually adding support for other safe for managed languages. Like I mentioned, I've seen 2 projects that have implemented like a Java virtual machine, and they do it effectively in Rust, right? Entirely in Rust rather. And while they use some unsafe code because it's running as a regular user-space process atop any OS platform, we can remove that unsafe code by implementing it directly within Theseus. So that's another possible future direction. Another thing that I want to explore, Lynn and I have had this dream of, using Theseus as kind of like an underlying systems layer for processing on edge computing nodes, right? And there's a lot of interesting things you can do. I mentioned already the support for like SIMD and a separate personality, which could be used to run like baseband processing workloads for cellular providers. I think another interesting thing is we could do, hopefully, is just general better efficiency, on edge nodes, and even do something like local streamed VR or AR applications. But yeah, I mean, I want to explore, I think, more heavy usage, and then finally, yet another example would be, using it in almost an embedded context. Even in data structures, like as the systems software for a top-level data center network switch. Right? That's something that really intrigues me. Those things have hardware redundancy, but they also need to be taken down when they're updated, right? So I think that we could provide some improvements beyond that state of the art. Those are some ideas. Anything else?
I have a curious question, more like hypothetical, but
yeah,
you could influence hardware design. Will there be any hardware mechanism that you will think will make the work of Theseus easier or maybe more performant?
Easier, yes. I didn't talk about it too much, but there's a lot of like in like the Intel architecture manual, you'll see so many references like system software must hold XYZ, right, on behalf of the hardware. And that is just a nightmare for state management, right? The problem is you may have to allocate it yourself, or it may live in some special area of the hardware that isn't really mappable with standard memory. And all of these things require special, weird workarounds to support. And I think a lot of this is due to just x86 being rife with legacy cruft, right? We have worked on an ARM port, and I foresee, I expect it to be way, way simpler in terms of state that needs to be held. But I will identify one particular area which I find particularly difficult, which is interrupts, right? The interrupt descriptor table, interrupt vector table, whatever you want to call it. This has proven difficult for a variety of reasons, right? In one case, right, on one hand, you do have to maintain this table of interrupt vectors. You could reroute them all to the same thing, but then there's a little bit of potential contention or reentrancy issues. If you want to allow dynamic registration of interrupts, you have to then keep a list of registered interrupts. All of these are forms of state that we have to manage, and I find it extremely annoying that, in particular, the limitations on what you can store in an interrupted vector table entry actually requires you to have a separate set of state and then link the two together. And that's really, really difficult to express in an intralingual fashion, right? Because the interrupt format, interrupt descriptor table entry format is like, you know, take the first 16 bits and shift it over here. Like, there's no way to relate those two. So I think it would be a lot nicer if, you know, you could, for example, in something like, you know, RISC-V, the new RISC processor architecture, maybe we could, you know, influence or look at different structures for holding interrupt vectors that allow you to insert maybe some arbitrary software state. For example, like page table protection bits do, right? There's a lot of changes I would make. Interrupts is definitely the biggest one. I don't even know if I really like the concept of like other x86 things like task state segments, which were previously used for hardware task switching, which is a huge mess and a disaster that it's just, I would love to get around. Yeah, none of these are really used in Theseus, but we still have to deal with them. So yeah, maybe there would be well, not maybe, there would definitely be a lot of changes I would make if we knew that the hardware wasn't providing isolation. And that's something we have discussed at length, basically relying on hardware only for performance improvement and not for isolation or safety.
All right. Okay, so we're close to 2 hours, the time limit. So any question from the committee member? All right. So Kevin, I think what you should do is you make me the co-host and you step outside, but watch your Slack, and I will pin you on Slack to ask you to come back.
Great. Okay, here goes.
You should make me calls. I think you should stop recording too.
Oh, sure. How do I do that? Sorry, oh, there it is. Okay.